In this video, we're going to look at calculations with equilibrium expressions. If you catch on to this method, you are golden till spring break. You can apply this to so many different kinds of equilibrium expressions. You're going to love this. All right, so let's see what we got. They'll always give you the balanced equation. That's handy. We have, at a certain temperature, a 1 liter flask that initially contains 0.298 moles of phosphorus pentachloride and a little bit of phosphorus trichloride. After the system had reached equilibrium, there's 2 times 10 to the negative third moles of chlorine found in the flask. We want to calculate the equilibrium concentrations of all species and the value of K. Fabulous. So here's how you start equilibrium calculations. Easy. Rewrite the equation. Like what? Yeah, just rewrite this balanced equation. We've got the PCl3. There we go. Cl3 and chlorine. Then down the side we're going to write ICE. These things are called ICE tables. You're going to love this. You can solve all kinds of equilibrium calculations with an ICE table. If you use these on the AP test, it's a good thing. You're going in the right direction. Okay, so I stands for initial. How much of these substances are initially present? Your options for units in this equilibrium ICE table are either like moles per liter or molarity. Concentration is dependent on the position of the equilibrium. Or pressure. They could give you partial pressures of each gas. Like they might say you've got, 0.5 atmospheres of chlorine or whatever. You can plug in to this ICE table using pressures or concentrations. Those are your only options. In this case, even though they're gases, we're going to use concentration. We've got moles in a 1 liter flask. So I'm going to just plug this in then as initially 0.298 moles per liter. Now we've got some phosphorus trichloride, which I think I'm going to take it out of scientific notation. That's not a super crazy number. 0.00880 moles per liter. That's an L. Notice that initially they don't mention anything about the chlorine. Initially, my flask has the 2 phosphorus compounds. After the system has reached equilibrium, here's the amount of chlorine present. So since they don't mention anything about the initial amount of chlorine, I'm going to put it in as 0. I'm going to assume maybe there was no chlorine initially present. And that's always a fair assumption. If they don't mention it, it must be a 0. Okay, so I stands for initial, super easy. C of your ICE table stands for change. We need to know 2 things. In what direction do we shift to reach equilibrium? And by how much? Well, one of those I can answer right away. I know this thing is shifting forward. We have to shift forward. How do I so quickly notice that we need to shift forward? Because of this. At equilibrium, you can't have any zeros. If this thing is going forward and reverse, you can't have any zeros. I mean, if we're going forward, we're going to make some chlorine. So we have to shift forward. You can always do that. If there's a 0, you'll always shift in the direction of the 0. Now, the only bummer here is that I don't really know by how much to shift. How far forward do I need to go until I hit equilibrium? Well, look at this other number given. After the system had reached equilibrium, 2 times 10 to the negative third moles of chlorine are found in the flask. Guess what? E of your ICE table stands for equilibrium. We do have 1. We were given the equilibrium amount of chlorine. And again, I think I'm going to just put it in as like 0.00200 moles per liter. E stands for equilibrium. So you have to watch the wording a little bit in the problem. The amounts given, are they initial amounts or are they equilibrium amounts? Well, if I know the chlorine started at 0, and I know the amount present at equilibrium, I know the change. This chlorine must have gone up by 0.00200 moles per liter. Well, guess what? Everybody else is going to change by that amount. Now we're going to change by the ratio in the balanced equation, which is kind of handy because this is all one-to-ones. If we're shifting forward and we're producing this much chlorine, because it's a one-to-one ratio, we're also going to produce 0.00200 moles of the phosphorus trichloride. So all you do is add. We're shifting forward. We'll take our initial plus the change, and we'll say at equilibrium, this is 0.0108 moles per liter. Well, that wasn't so bad. Okay, so now if we're shifting forward, the reactants are going to go down. And again, since it's all one-to-one ratios, we're going to decrease by 0.00200. So that at equilibrium, this is going to be 0.296 moles per liter. There you go. There's an ICE table. You're going to love ICE tables. Initial, change, equilibrium. We knew it had to shift forward because of the 0. And since we knew the equilibrium amount of chlorine, then we could figure out by how much we're shifting forward. Everybody shifts at the ratio in the balanced equation, 1-to-1s in this case. The products will go up by 0.002, and the reactant will go down. We've answered half of this question. The equilibrium concentration of all species, there they are. E stands for equilibrium. So the last thing they want then is the value of K. K equals products over reactants. So we're going to have 0.0108 moles per liter. That's the phosphorus trichloride. Get out of there. PCl3. I don't know why I did that again. That's to the first. Then we're going to have the chlorine. 0.00200 moles per liter for the chlorine. To the first. All over 0.296 moles per liter of the phosphorus pentachloride. To the first. And now in this case, I get it. This is super easy. You could just plug this in your calculator. Products over reactants, they're all to the first power. But you have to show this setup. You have to show your work. I get, again, even this ICE table. You might have been able to do this in your head eventually. I mean, if you know that it's going to change forward, you notice that one of the concentrations was given at equilibrium, you know by how much everything else changes. You have to show your ICE table, and you have to show this setup for K. Otherwise, you get nothing. And again, since these are kind of easy, you want to get all the possible credit on a problem like this. If I plug it in my calculator, K equals, let's go 7.30 times 10 to the negative fifth. There she is. And, why do I have K equals? K really equals. There we go. 7.3 times 10 to the negative fifth. You do not need units on your K value. This is a great example of how to set up an ICE table. Now, this would maybe be an easy one, where we're given a 0, so we know it shifts forward. We're given one of the equilibrium concentrations, so we know by how much we're going to shift. Let me show you how we could make this more fun. Check out this guy. We're still given the balanced equation. That's a good thing. Let's see here. At 700 Kelvin, good Lord, the equilibrium constant is given to us. K equals 5.1. Calculate the equilibrium concentrations of all species if 1 mole of each component is mixed in a 1 liter flask. All right, so we're going to ice table this thing. I mean, if you ever get an equilibrium kind of problem, that's your first thought. Let me set up an ice table. Okay, so we've got our equation. Carbon monoxide and water. We've got carbon dioxide and hydrogen. Then we're going to ICE. I stands for initial. Initially, we have 1 mole in a 1 liter flask. Well, that's easy. 1 mole of everything per liter. 1 mole per liter. 1 mole per liter. And 1 mole per liter. Excellent. And again, we could do this with pressures, but we are given concentrations. Uh-oh. Okay, so C is change. We need to know the direction and by how much. There are no zeros. Dang. When you have a zero, it's great, because then you automatically know you got to shift in the direction of the zero. You can't have a zero at equilibrium. If you don't have zeros, you got to do this. Q. You got to calculate Q. With the amounts given initially, let's compare Q to K. So we set up what looks like an equilibrium expression, but it's going to have initial data, which, I mean, I might just plug this in as 1 mole per liter products over, oh, I bet you can see where this is going, mole per liter hydrogen. La, 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 la. And they're both going to the first power over 1 mole per liter of the carbon monoxide and 1 mole per liter water. Everything's to the first power because it's all a 1-to-1 ratio. And this is brutally easy. Do I have to show this work though? Yes. I do somehow need to show how I solved for Q. Although this is very easy. Q equals 1. I like that. 1 times 1 over 1 times 1. Which I suppose I could have been a good sig fig person and put this in as 1.00 if that bothers you. Q is 1. So we compare Q to K. K is given to us. Q is smaller than K. And remember that these are always a comparison of products over reactants. Q is too small. So to reach the equilibrium constant, we need to make Q larger. How do we make Q larger? We need to favor the products. So if we favor the products, we're shifting this thing forward. We're going to shift forward. Okay, so if you don't have a zero, you have to calculate Q. Using the initial conditions, compare Q and K. If Q is too small, how do we make Q bigger? More products, less reactants. We're going to shift forward. But now here's the other bummer. We don't know any of the equilibrium amounts. It's all we're given, just the initials. So I know I need to shift forward, but I don't know by how much. In the last one, we knew one of the equilibrium conditions, so we could kind of backtrack and figure everybody else out. This time I don't. I don't know anything at equilibrium. All I know is I got to shift forward. Let's call it X. I mean, we could just pretend all day to try stuff until we plug it in and K equals 5.1. But let's just say X. I mean, if we shift forward, these are a 1-to-1 ratio, so they'll both go down by a certain amount, and then my products are going to go up by a certain amount. 1-to-1 ratios. If this was a 1-to-2, then we might have like X and 2X or something like that. So that at equilibrium, this is going to be like 1 minus X, 1 minus X, 1 plus X, and 1 plus X. All I need to do is solve for X, right? If I can solve for X, then I know the change, and I can change then from the initial. How do we solve for x? Super easy. We just need to do a little algebra. Your algebra teachers from years past are going to be so excited. When am I ever going to use this stuff? When I set up ice tables! Okay, so we know K. K is 5.10. K is products over reactants. So let's just set this up with our variable. So our product, these are each 1 plus x. 1 plus x. And they're both just to the first. That's a good thing. It's going to make this really easy. And then my reactants 1 minus x and 1 minus x. Excellent. Excellent. Okay, so what are we going to do here? Really, we could kind of write this as 1 plus x squared over 1 minus x squared. We could kind of simplify that. And then could I simplify this even further by maybe like taking the square root of both of these? Okay. So let's take the square root of 5.1. And I get about like 2.26 equals 1 plus x over 1 minus x. So we just need to solve this thing for x, right? Okay, so let's cross multiply. 2.26 minus 2.26x equals 1 plus x. We can simplify this further. We'll combine like terms. So let's subtract the 1 and say 1.26. And then we'll add this. So we'll get like 3.26x on this side. I can solve this then for x. 0.387. How about that? These are going to be fun. Like, I know you're not going to want to admit it, but some of you are really going to think like, ooh, I like that. That's actually kind of fun. Hey, guess what? If we know x, we know our change. And if we know our change, we can figure out the equilibrium concentrations. All we got to do then is take x and sub it in once, twice, 3 times, 4 times. So here we are at equilibrium. These are going to be the same. The carbon monoxide and the water on my reactant side will each be 1 minus x. How about 0.613 moles per liter? And then on my product side, I've got carbon dioxide and hydrogen. That'll each be 1 plus x. 1.387 moles per liter. Done. So, this is kind of as bad as it gets. Where, number 1, we don't know the direction of the shift, so we have to calculate Q. Using our initial amounts, we'll compare Q to the real equilibrium constant K. That should give us the direction of the shift, and then if you don't know by how much, just plug it in as x. Then you can set up an equilibrium expression to solve for x, as long as you know the value of K, which you will. In a problem like this, you will know K. Solve it for x, you know your change, then you can go apply that to your equilibrium conditions. Okay, so I know you may have had a little fun doing this one. I'm hoping that this method will start to click. This really is about as bad as it could possibly get.